start the recording. Yeah. And I'm going to share my screen. All right, let's make that go away because I don't like to see me. I'm going to not let you see me because you don't need to look at me. You should look at the math. Okay, so what we're doing today, our exam 3 review has 20 questions, just like all the others. If you could do these 20 questions, you'll be fine on the exam. The exam will have 15 out of these 20 questions. There is not what I thought there would be here. I'm going to add to this. Oh, I know why. There's supposed to be a review here. Maybe not on the exam review, but I posted this on Blackboard for you as well. This is just the fastest way for me to get to it. So I posted this on Blackboard in the week 15 folder. I posted information on how to work on the track tricks, and I posted this yesterday. And these rules for inverse trig, hyperbolic, inverse hyperbolic, and the like. Wow, there's some weird noises going on in the LC today. So this will be a handy sheet to have just so it's quick. If you already have them written down, don't worry about it. But I did post that on Blackboard for all of us. So what I'm going to do is turn this video back on because I'd really like to see you guys, if not me. I thought maybe we wouldn't do a problem if we were all cool with it. So we're going to use the thumbs up, thumbs down idea. Probably just a thumbs up because I'm a positive kind of person. Would anyone like to discuss problem number 1? 5, 4, 3, 2, 1. That's what I was thinking. Now, these are pooled questions, right? So I have several other people's up here. Here's a number 1 that is different from mine. Would anyone like to see this problem worked out? Fantastic. That's much like mine, much like mine. And so it looks like it's going to be essentially these two different types of problems for number 1, if number 1 shows up on the exam. So let's take a look at number 2. I'm hoping you're a little impressed that I have all this ready because it took some thought. I'm just kidding. We're good. Use the upper and lower sums to approximate the area. Would anyone like to see this problem? All right. That's what I assumed. I assumed there'd be multiple of you. I should have just started on it right away. Okay, so I'm going to just copy this part of it so we could see the math big. So we're going to use upper and lower sums, and we see here that we have 1, 2, 3, 4, 5. So our n value is 5, and I made this really thin yesterday because it was annoying me, but we'll go back to the regular size. All right, so n equals 5. Upper and lower sums. As we look, which one is right and which one is left? I'm going to look at the most obvious. So on the right-hand side, this would be a lower. So right-hand side is the lower side because it's a decreasing function. So on the right, the function is lower. But if I use a left-hand endpoint, right, we're going to have an upper sum. So left-hand side. I like to get that in my head because I'm using left and rights of endpoints. Also, if the interval from 0 to 1 is cut by 5, we have 1/5, 2/5, 3/5, and 4/5. So our upper sum, we'll go upper over here. Our upper sum will have a width of 1/5 multiplied by all these different heights, right? So it's 1/5 times f of upper is left. So 1/5 times f of 0, 1/5 times f of 1/5, 1/5 times f of 2/5, and so on. So I'm just going to factor out that width. So I'm going to write it in detail. So all the left endpoints and this big parenthesis, which becomes, I'm going to assume that this is f of x instead of y because f notation makes sense. Function notation makes more sense. F of 0, when I put in 0, I get the square root of 1, which is 1. 1/5 squared is 1/25. This will be the square root of 24 over 25. Let me show you why. I'm just going to do this one probably. I might do the other ones. We'll have 1 minus, and that's not true either. I know, some of you already noticed that. 1 minus 1/5 squared is 1 minus 1/25. But 1 is 25/25 minus 24/25 becomes 1/25. No, how about Tuesday pay attention to what she's doing and write the real work and not the backwards work. This is still 1/25, nothing changed there. This one's the 24, all the right numbers, all the wrong places. So if this is all under a square root, we'll have the square root of 24 over the square root of 25, and the square root of 25 is 5. Yes, we can simplify this. No, I don't care to. 2/5. So 2/5 squared will be 4/25. 25 minus 4 is 21 under the radical, square root of 25 in the denominator. 3/5. 3/5 squared will be 9/25. 25 minus 9 is feeling very 16. Square root of 16 is 4. So we have 1, square root of 24, square root of 21, 4/5. The last one, if I square 4/5, I'll have a 16/25. So 25 minus 16 is 9/25. The square root of 9 is 3. Square root of 25 is 5. And now we will put this in a calculator because our brains have done the hard part. We'll let our technology do the easy part. So 1/5 times 1 plus the square root of 24, come out of the radical divided by 5, plus the square root of 21, come out of the radical divide by 5, plus 4/5 and 3/5 make 7/5. And we'll close our parenthesis to get 0.85926. We're looking to 3 decimal places. Hopefully that's what I said. It looks like 0.859. Now, how is this going to change when we're doing our lower sums? The only thing that's going to change is we'll have 1/5 times the right hand values. 1/5, 2/5, 3/5, 4/5, and ran out of space, f of 1. Let me make this one wider for next time too. So it's going to be the exact same thing. The only thing that changes is for left-hand side, in this case, upper sums, we use the left endpoint 0. But for the right-hand side, we use the right-hand endpoint. So the only way that this is going to change, really, let's not redo any work. This 1 won't be here, but I know exactly what these values are. I'm not going to use valuable time on my exam to redo stuff that we already know. I mean, we already wrote it one time. We might as well leave it like that. What's f of 1? When I put 1 in, I get 1 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. So it looks like we ended up just losing a 5th. So this answer should be, don't try this at home. A 5th is what, 0.2? I'm going to guess the lower sum was 0.659. Let's just see how I did. I'm going to put this back down. maybe. I don't know. Let's see how we do. Yes. Good news. My brain's coming back, getting rid of that fog. All right. Does that make sense? There you go, so you can see more of that. All right, let's see what other number twos we might have. Oh, midpoint rule. We should take a look at this one as well. I think these are the only two kind of things we got going on. I swear I didn't cheat. Yes, that is the same problem. Midpoint rule. Yeah, so let's take a look at 2 tangent of x from 0 to pi over 3. It's the same idea, right? I'm going to break that over here. This is number 2. This is also a number 2. All right. Let's get organized. I'm going to leave the answer there. I mean, why not, right? Guess what Tuesday did? Tuesday screwed up. All right, hold on. Control Shift H. Make that go away. And then I want to sorry, I forgot to give myself more paper. And once I start writing with the pen, I can't add pages later. So I'm going to take this whole thing. Hopefully. Come on. Need to do it. All right, I'll leave space for it there. We're going to put our new number 2 here. My goodness. My goodness, people. I was just not prepared for this, was I? I was all excited, just sitting here, just waiting. And keep the answer. There we go. All right, I'll put in that other stuff later before I post it for all of you. So let's go big again and work through this one. The midpoint rule is a little more challenging, right, than our endpoints. So we have to use the midpoints. N equals 4. So I'm starting at 0. I'm ending at pi over 3. And I want to cut this into 4 pieces. So the first one easily is half of that. That's pi over 6. And if I cut this one in half, we'll have pi over 12. If I really think about it, I'm going to go back to this tiny writing here. We'll have 1 pi over 12, 2 pi over 12. So we'll have a 3 pi over 12. And this is 4 pi over 12. Now I use what I call a cheater's method. Remember 3 pi over 12 simplifies as pi over 4. I use the cheater's method of just cutting it in half and half and half. But if you have n equals 5, the way we get our value, our delta x, it's always the length of the interval divided by the n value. Instead of dividing by 4, we can multiply by 1/4, and that's really how we get the pi over 12 algebraically rather than conceptually. But either way is going to be just fine. It works exactly the same. All right, so we know where we want to evaluate it. We know the width. So just like before, I'm going to call this midpoint though, we'll have the width of each one. And now we'll need the height. But we're not looking at the left endpoint or a right endpoint. We're looking at a midpoint. So in between 0 and pi over 12 is pi over 24. In between 1 pi over 12 and 2 pi over 12, all right, think about it like this. This is 2 pi over 24. This is 4 pi over 24. So we'll have a 3 pi over 24. So it's 1, 3, 5, 7. All right, 1, 3, 5, and a 7 pi over 24. So I'm looking at bigger thickness. 2 tangent of pi over 24 plus 2 tangent of 3 pi over 24 plus 2 tangent of 5 pi over 24 plus 2 tangent 7 pi over 24. And of course, we're going to use a calculator on that. I don't happen to know tangent of pi over 24 on the top of my head. So we'll take pi divided by 24. Pi divided by 12, that's our width. 1 width, pi over 12. And then these are the midpoint heights. So times 2 tangent of pi divided by 24 plus 2 tangent of a 3 pi divided by 24, and so on. And I want to make sure that this works out to the right answer, or else I would stop and not waste your class time typing into a calculator. But sometimes it's really important to me that we get the answer right, because I know I've given you answers that were wrong before and I felt so bad. And in the parentheses here as well. And that's how we get the 1.370. Fantastic. All right, so that's exactly the way it works out. So you could do left endpoints, you could do right endpoints, you could do midpoints. It's all the same. Once you have your width, you just find and use the correct endpoints. All right, let's throw this down over here and come back. All right, back up so I can see you again. How are we doing on number 3? Okay, so the square root of 16 minus x squared, this is always going to be a circle. The top half of a circle, so it's going to be a semicircle. Especially when it's from -4 to 4. So it's not either of these two graphs. It's one of these two. Which one? Well, the one that tops out at 4 as well, because we can never reach a y value of 16, right? When x is 0, the square root of 16 is 4 is the highest it can go, and that's how we know it's this graph. Now it says use a geometric formula to evaluate instead of using a, we can't do a use substitution with this. This is a different one. You know that the area of a circle is pi r squared. And if this radius is 4, that's 16 pi, but that's for a full circle. So half that circle would be 8 pi. My question, I believe, is different, however. So we want to sketch the region whose area is given by the definite graph. So the first thing I would look at is -9 to 9. So it's not these two, it goes all the way to 10. Good, top ones. 9 minus the absolute value. All right, these graphs are exactly the same in every other way except for the shading. The shading goes from -9 to 9. This one goes from 0 to 9. It's not that one. -9 to 9 would be this graph. If I wanted to use a geometric formula to evaluate the integral, how do we find the area of a triangle? It's 1/2 the base. So the full base is 18, half the base is 9, times the height. Right, half base times height. 9 times 9 is 81. Yeah. Let it be easy. It's either going to be an absolute value or a semicircle, so a triangle. Don't forget your basic geometric formulas now that you know all this fancy calculus stuff. We are going to do one of these number 4s. Let me look. All right, this is mine. Somebody else's number 4. Yeah. Okay, we'll do a couple of number 4s. Oh, I was just showing something yesterday. That's not an actual answer. So as I'm evaluating the definite integral, it says use a graphing utility to verify your results. Of course, we would never do that in a class where graphing utilities are not allowed. Let's do this. Just move this over here. To make it so we can work on it. So as I'm looking at this particular parabola, right, I know that the vertex is at negative b over 2a, which is 6 over 2, which is at 3. So this goes from 0 to 8, but what I know about this is it's a parabola because it's a squared, and it opens up. So the graph opens like this. My vertex is at 3. So I guess I really need to know where the y value is. If it's below the axis, we have an issue. If it's above the axis, there's no issue whatsoever. So when I put 3 in, 9 minus 18 is a negative 9. Yeah, so it's a negative 4. So we're in a situation like this, and our actual graph will turn out to be, let's put it in blue, right? The absolute value portion pops up. But we need to know where this hits. Where is our 0 point here and here? If we're looking at x squared minus 6x plus 5, I can factor. X minus 5 times x minus 1. So I know that this is at 1, this is at 5. And we can rewrite our big integral as from 0 to 1, it's just the parabola. And then from 1 to 5, it's the opposite, right? A regular parabola would be down here. If I use a negative, I flip it over the x-axis, and so it'll be this portion up above. So I'm going to subtract x squared minus 6x plus 5 dx on the portion that's flipped up, and then finish it out from 5 to 8. This is our key right here. Using the negative portion to flip this up. So using the minus of the original, and that's the only thing that's going to change with this absolute value. I'm not going to finish this problem because you all know exactly how to do this. You really do. Polynomials, you could do those integrals all day long. Not that you'd want to, but you could. Okay, let's look at the rest. Absolute value. What was I looking at? The indefinite integral. Remember, you'll have this formula sheet. I encourage you to print it off. That's not the one. I guess there's nothing to print off on this other number 4. Another number 4 says I want the area under this curve. And secant is reciprocal of cosine, right? If my cosine graph goes like this, then my secant graph will go like this. We'll pretend I hit that one. Right? My secant graph happens to be even. This happens to be 2 times the antiderivative from 0 to pi over 6. Because it's even, we really only have to do that half the interval. 2 times 5 is going to make it 10. And we ask ourselves, what has derivative equal to secant squared? Tangent does. So this will be 10 tangent of pi over 6. Yep, and the tangent of pi over 6 is square root of 3 over 3, which is the correct answer. All right, so they're very similar, but slightly different. This one is getting at the idea of even and odd, whereas this is looking at how we can use a negative when we reflect part of the graph using absolute value. Right? But both is, kind of the same concept, slightly different approach. Number 5. I think on number 5, the hardest part is knowing how to write it up on this one. But remember, we're going from 0 to pi, our x values, that's the value on the integral. It gives you the function, and then you just evaluate. So I'm not going to look at this number 5, but I am going to look at my number 5. My number 5 says we want to use the mean value theorem for integrals. So if you have to look up any formula as you're doing this review, make sure you have quick access to it on Thursday as you're doing the exam. Right? I would look up all my formulas and just kind of have them close. Write them down on a piece of paper. You might never need to look at them, but they'll be near you so that if you do need them, they're there. I'm getting tired of black. Let's go with orange. Mean value theorem for integrals. This says that the mean value is 1 over b minus a, the integral from a to b of f of x dx. All right, so there's a value c for which this function has this particular height, because this is the area divided by the width will give us a height. Here's our function. So a and b minus a is 9 minus 4, which is 5. So I need to find an f of c that is equal to I need to find an f of c that's equal to 1/5 the integral from 4 to 9 of 2x to the 1/2 dx. Well, I can find this integral. I'm going to put that 2/5 out in front. All right, take that 2, its coefficient, and the power rule for integrals says we add 1. So this will be x to the 3/2 divided by 3/2. And we're evaluating this one from 4 to 9, so we don't need that plus c. I'm going to rewrite this. Instead of dividing by 3/2, we multiply by 2/3. I'm going to rewrite it like that. That is 4/15 times 9 to the 3/2 minus 4 to the 3/2. 4/15. The square root of 9 is 3. 3 cubed is 27. The square root of 4 is 2. 2 cubed is 8. 27 minus 8 is 19. Yuck. 76 over 15. So what we're saying here is there's some f of c that equals 76 over 15. So 2 square root of c equals 76 over 15. Did I multiply that right, by the way? 19 times 4. 20 times 4 is 80. But it was 19. Let's just subtract 4. Hey, I trust that. So we're going to divide by 2. I'll have the square root of c is, if I divide both sides by 2, the 76 gets cut in half. Half of 70 is 35. Half of 6 is 3. So 35 and 3 is 38. We'll move it this way. We're going to square both sides. And 38 over 15 squared. I guess I'll turn my calculator on first. 38 divided by 15 squared. Excellent news. It's between 4 and 9, and that's exactly what I wanted. 4 decimal places. So we're looking at 4178. All right. Does that make sense? We good? Fantastic. Thank you. All right. Excellent. Excellent. I'm not paying attention to the clock at all, and that's not good. We're on number 5. Number 6. We're going to use a U substitution. When U equals 5 minus x squared, our derivative will be 2x, so we'll be able to take care of that x. Our inside of the parenthesis, at both places, both the examples we have here, take what's in parentheses and make that your U value. I haven't scrolled this one in a minute. Yep, what's in parentheses. What's in parentheses. So it's all kind of the same thing. U substitution again. U equals x over 2. The antiderivative of cosecant squared is cotangent. Make sure you adjust. Where did that minus 2 come from? It comes from that du replacement. My version. We're going to let u be cosine. Sorry, I got to kick it up a little bit so we can get through the whole thing in the 15 minutes we have left. I'd let u be cosine because the derivative of cosine is sine. It takes care of that sine x dx. We'll have u to the negative 4th here. I could actually get this one down. U to the negative 4 becomes u to the negative 3. So we will have secant. Oh yeah, that won't work. Maybe. Secant of x to the 3rd plus c. All right, I'd have to work it out. That's a good guess though. I don't hate it. I don't hate it at all. This is a logarithm. I don't expect you to have algebra on your exam, but you could totally, you could expand this, right? Let's not forget our algebra skills that you guys are actually really good at, because you're really good at calculus. In order to be really good at calculus, you have to be good at algebra. Let's see, go back to orange. I would first rewrite. And then I'd move that power in front. And then I would use the quotient rule that says the natural log of a quotient is the natural log of the difference. Is the natural logs of the differences. I don't know what the grammar with that is, but that's it. That's all we're looking for. If you want to distribute your 1/2, you can. If you want to leave it out front, that's fine too. Don't overthink this problem. Remember, to find the derivative of a log function, it's just the derivative of the inside divided by the inside. What do we got on 8 and 9? Oh, so in the other option is they'll give you this, and you need to tighten it up and write it as a single. And it's annoying. It is. It's hard. This is whoever's we're looking at. I made sure to hide the names. Great job writing that in. Derivative of the natural log, right? So we need to know our trig derivatives as well. There's a chain rule kind of going on. The derivative of the inside divided by the inside. Let's do an implicit differentiation. Let's look at number 10. Ooh, logarithmic and implicit differentiation. So let's do a logarithmic first, because for me it's more fun, which generally means it's one of the more difficult concepts. I don't know. I really like it when I understand a difficult concept. Use logarithmic differentiation. We have 3 steps. Step 1, throw a natural log in front of both sides. Step 2, simplify that right-hand side. If it was in the numerator, it's going to be positive. If it came from the denominator, that quotient rule, right? Exponents in the denominator are negative. All logarithms are is exponents. So anything that was in the denominator will have a negative in front of it. No powers, so I don't have to worry about numbers out in front. I guess it's a 4-step process. Step 3, take the derivative. Implicit on the left. On the right, super easy log rule. The derivative of everything inside is 1. So this is 1 over x plus 1. This is 1 over x minus 2, right? Our derivatives of logarithm is just the derivative of the inside divided by the inside. Derivative of x minus 1 divided by x minus 1. The derivative of x plus 2 divided by x plus 2. Step 4, I do it the lazy way. It's a quit while you're ahead algebra approach. I know that I could screw up the simplification of this in many, many, many different ways. I'm going to multiply both sides by y here, right? Where am I going? Let's make it thin. So I'm going to times y. I'm going to times y. So instead of multiplying by y, I'm just going to rewrite the original. And if I had patience, which I don't, I would type that all in and show you that it all worked out. But no, I don't have the patience for that. We don't want to waste our remaining class time on something like that. This answer will suffice. If you want to simplify, feel free. If you don't want to simplify, I'm cool with that. Totally cool with that. What was the other one? It was implicit differentiation. So same idea. These are some of the more challenging, which means also more important techniques. So I want to show you these ones that are not standard. We didn't have a lot of homework, a lot of practice on them. At least in this one, we have the answer already. That's cool. All right. So we're starting with the natural log of xy plus 4x equals 15. We want to use implicit differentiation. So the derivative of the natural log is the derivative of the inside divided by the inside. Derivative of 4x is 4, derivative of 15 is 0. Now, I didn't really do anything here because I didn't find what the derivative of xy was. But the derivative of a product is first derivative of second plus second derivative of first. I'm going to put this in here. So I'll have x dy dx plus y all over xy plus 4 equals 0. So if I am adding over a common denominator, I will have x dy dx. No, that's an aside. That's my scratch paper. Divided by xy plus y divided by xy plus 4. Cancel, simplify. We'll have dy dx with a 1 over y, right? dy dx could be in the numerator, or it could be next to it, right? It can be next to the fraction, just can't end up in the denominator. X is canceled out. Here my y's cancel out. I want to get dy dx on its own. I will subtract 4, subtract 1 over x, and then multiply it all by y. And yes, there's a tighter way you could write this up. It's probably like a negative y times 4x plus 1 all over x, I think. X negative. Yeah, that'll work. But this is a fine answer. This is a great answer. I love this answer. This is the answer that I would type in, because you know, you're in a hurry. You're gonna forget this negative sign. You're gonna do something silly if you try to keep simplifying. Oh look, it's right there. If I left the y factored out, yeah, it would have been all right too. All right, any of these three answers will work. I like how my computer keeps asking, hey, you sure you don't want to save this yet? No, I'm going to continue to be stupid and not save. 10 halfway through. U substitution. Go to mine, not somebody else's. U substitution, let u be natural log of x. The derivative will take care of that x in the denominator. Now we're looking at areas of regions. So now we're looking at integrals. Anytime you see the word area, it's an antiderivative. So this number 12 will translate directly into this antiderivative, the x0 to 2, our function, and it's always going to be a dx because x will be our variable. So we can find this. Do we know the antiderivative of secant? What has derivative equal to secant? We don't know that, do we? Well, this is a bad question for your exam. I would absolutely pull up a grapher and I would graph it to secant. So we're going to divide by cosine of pi x divided by 6. Right? That's an appropriate secant graph, so I know I entered it quite accurately. And then over here in calculate, I want to find the integral, so number 7, from 0 to 2. Puts that shading in for me, and it's 5.0304. We want it to 3 decimal places, and so this will be 5.030. Work smart, not hard, always. Always. You can find the derivative of the cosine function, right? Use substitution in order to make that happen. Is it always positive? Is it always negative? Does it change? It cannot be determined. You know trig functions. You can find the derivative of this because e to the x has derivative e to the x. Use a u substitution. Always the exponent of the e is our u substitution. Oh, remember the only thing that changes, and over here I have a different page too. This one I copied right out of the back of the textbook. That's all. That's why it's all weird. Check it out. It has all of your rules all together, and it has summary of important formulas. Look at that, a to the x. So we know how to find the derivative of 7 to the x. It's the natural log of 7 times 7 to the x. table of integrals. All right, so we can find all sorts of integrals. And I apologize for that being such a bad copy. So here's some geometry formulas and a table of integrals, just copied really bad. I could probably get a better copy of that for you right now. You know, technology being what it was and this website being put up about 6 years ago. So we can find these integrals as well. Inverse trig. Ooh, let's do number 18. All right. Find the indefinite integral. We got 3 minutes. Here's what I'm thinking. I'm going to use a different color. I'm going to let u be cosecant squared of x because it's in a denominator and it's inside a radical and it's ugly. I know the derivative of, yep. Well, as soon as I get here and I see this is going to be 2 cosecant of x, derivative of cosecant is cotangent, but it's a negative cotangent. Well, that's not so bad. I'm good. I'm not going to take that negative with me. I'm just going to take the 1/2. I was afraid that I was going to get a absolutely horrible derivative. That doesn't seem right. You bring down the 2, you leave the inside alone, derivative of the inside. Yeah. Okay. Nope. That's not right. The derivative of cosecant is cosecant. Oh my goodness. Cosecant cotangent. So this is not true. And once I find out that it's going to end up being cosecant squared, trust me on this here, that means that I can't use this. So I try something else. So this is going to be a no, because the du doesn't work. And it's about that time I think to myself, square root, don't get a u squared, probably an inverse trig. So I'm going to let a squared be 9, so that a equals 3. U squared is cosecant of x, so that u is cosecant of x, because derivative of u is minus cosecant x cotangent x, and things fit a little bit better. Always go with the easiest possible way, but make sure it fits. Make sure you do your derivatives right. If it doesn't fit, now we're looking at minus cosecant x cotangent x square root of 9 minus cosecant squared x dx equals, yeah, there's a division there too. That minus, let's see, I'm going to rewrite this as du, right? Minus cosecant x cotangent x is our du. Square root of a squared minus u squared. And I ask myself, where have I seen that formula before? That's why I brought it back here. I was looking at antiderivative. Oh my goodness, seriously? Yeah. I'm sorry, my head's really just not in it. Okay. When we have a squared minus u squared, we set up the arc sine formula. This will be arc sine of u over a plus c, and we reverse our substitution. This is arc sine of cosecant x over 3 plus c. Wow. Wow, that's ugly. I'm not going to bother putting it in there. I am going to put it in here. Arcsine of cosecant x divided by 3 plus c. Fantastic. I like to get at least the last one that I entered in correct. It is 11:22. I apologize. If you need to go, you go. It's cool. The derivative of a hyperbolic trig function, we have these here. Use the formula sheet. Find the indefinite integral. We have the formula sheet here. Make sure you have it with you. You'll be just fine. We've done so much in chapters 4 and 5 so quickly, and in such a weird way because I've been gone for the last month, but you guys know how to do this. You really do. I think you'll find that for most of you, exam 3 will be your highest grade. Hopefully the final will be, but most likely exam 3 will be your highest grade of the exams. For those of you that are here, do you have any specific questions you want to ask before we let you go? I'm going to stop the recording.